All right, so Unit 8, Day 2, significance testing. And this is the review from last class. So this is the problem we're going to do. You can take out some paper. If you need some paper, I have some over here. If you need a pencil, I have some over here. So a politician claims they vote with the majority 85% of the time. You check the last 200 bills for passage. Where should the sample fall? So basically, what is going to be our confidence interval so that you can be 95% confident that the politician was telling the truth? Okay, so for the first part, finding the standard deviation, we're going to use our standard deviation formula. What number did you use for P? 0.85, good. And what did you use for N? 200, very good. All right, and so then if you use Desmos and do this all in one step, you should get 0.02525. For the next one, to find your confidence interval, you need to take your 85% or your 0.85, and you need to add 2 standard deviations and then subtract 2 standard deviations. So you would get these numbers. So they were rounded to 0.90 and 0.80, which is 80% and 90%. And then to interpret the confidence interval, you're just going to write your confidence statement. Actually, and some people, this one's not written exactly like that. Some people wrote, I'm 95% confident that it would land between 80 and 90%. And that means that if it landed between 80 and 90%, we would believe the politician's claim. Who has a question on that? On the process or on the meaning of what we did? Okay. So here's a question that you might ask yourself. Why do we need a confidence interval? Why can't we just check the 200 votes and see if he claimed with the majority 85% of the time? What do you guys think? We did check the votes, right? We checked 200 votes. Would you expect that it would be exactly 85%? Might be. See, what did you have to add?
I was just gonna say that like it would take too long.
It would take too long? Yeah, it does take a long time to check all of the votes. We ended up checking 200, but if we wanted to check all of the votes in all time, that would be even more. So that's a good reason why we do take a sample, so that, because sometimes checking an entire population is either impossible or just take a really, really long time. So yeah, we do need to take a sample sometimes, and we took a sample of 200 votes, and that sample will not always be exactly the same as the entire population. So we expect some variation, and this margin of error that we found lets us know what's a normal level of variation if he really does vote with the majority 85% of the time. So we would expect the answer to be somewhere between 80 and 90%, might not be exactly 85. All right, this slide has a lot of words. So confidence intervals, that's what we just did, are one of the 2 most common types of statistical inference. Researchers can use a confidence interval when their goal is to estimate a value for a population based on a sample. And that's what we just did. We took a sample of 200 bills instead of looking at every bill that this politician ever voted on. A second common type of inference is called a significance test. That's what we're talking about today. It has a different goal: to assess the evidence to verify or to disprove a claim concerning a population. So we have an example there. In the example, it says 50% of marriages in the US end in divorce. We can't check every single marriage, but we can collect a sample to see whether or not it supports the claim. So significance testing does not prove anything, it just shows how likely it is to be true. All right, in significance testing, we identify a null hypothesis and an alternative hypothesis. The null hypothesis says that there is no significant difference between the sample and the population, which means that the claim is likely to be true. The alternative hypothesis says that there is a significant difference between the sample and the population, so the claim may not be true. We reject the null hypothesis. And it says the same thing down here. So using our example about 50% of the marriages ending in divorce, what would our null hypothesis and our alternative be? Remember, the null hypothesis says that there is no significant difference between the sample and the population. So what did we say about the population? What percent of marriages? 50%, yes. So your null hypothesis is that 50% of the marriages in the US end in divorce. And then your alternative hypothesis is the opposite. What would that be? So basically not 50, right? It could be more, it could be less. Okay? 50% of marriages in the US do not end in divorce. Okay, so here's a new idea. It's called a p-value. There are a lot of things called p in probability, but this is the p-value. To test our hypothesis, we need to calculate the p-value. It's the probability any correlation between our sample and the population did not occur by chance. I think the picture is super helpful in understanding the p-value. I'm going to go to the picture to show you. So we know the normal curve here. In the middle of the normal curve is where you would expect the population to be, where you would expect 50% to be. Your p-value is this area to the right of what you get from your sample. So you would want your p-value, you would want this line here to move closer to the middle. So if I'm moving it closer to the middle, do you want it to be larger, that blue area, do you want that blue area to be larger or smaller? You do. You want it to be larger because basically as this line moves to the middle, you get a larger area that's blue over here, okay? So we have a number that's going to be our significance number, and this number is related to your 95% confidence interval. It's 5%. So basically, you want this blue area to be bigger than 5%. Okay, if it is less than 5%, that means that your sample is way too far from what you expected it to be. If you have less than 5%, it's going to be over here, way off on the side. All right. So we are going to use z-scores, and it's related to the z-scores we did before, but not exactly the same. In the z-scores we did before is x minus mean over standard deviation. So it looks a little bit similar. This is going to be your sample percentage written as a decimal, and your claimed percentage divided by your population standard deviation. And then this is just a reminder of what standard deviation is over here. It's not part of that formula. This here means absolute value. So if our sample showed that 480 of the 1,000 marriages ended in divorce, what would the testing z-score be? All right, so what I want you to do now is find out 480 out of 1,000. What's that as a decimal? That's your sample value. Our claim value is 50%, 0.5. And then the standard deviation, I don't think we found that yet. So you also have to find your standard deviation over here. So take a minute and a piece of paper and see which of those you can find out. You can start with your standard deviation if you want. I know that there's two different numbers here that could be interpreted as percents. You're going to use the claimed value. So you're going to use the 0.5 for your p here. Okay. All right, so we subtracted 0.48 minus 0.5. We divided by our standard deviation, 0.0158, and then we took the absolute value. And here's what we're getting. We're getting 0.12649. So a lot of you had that, and that's good. If you didn't get that far, that's okay. It's a process. We'll get there. What questions do you have on the steps there? Okay. I'm going to the next slide, but if you have my slides open, you can go back anytime. All right, so what you're going to do next is you're going to open the z-score table, And we're going to use the number we find on the z-score table to find the actual p-value. Z-score tables go to 2 decimal places to the hundredths place. So if I round this to the hundredths place, that 4 is not big enough to round up. So I'm going with 1.26. All right, some of you are good at using the z-score table and some of you are still learning that, and that's okay. But what I want you to do is open the link. This is going to show up weird on my video. Open the link for the z-score table. And we're going to look for 1.26. Here's your link. You can also Google z-score table. There are a billion of them out there. All right, I'm going to try to make this a little bit bigger. Oh, I can't because this is in the way. If I move this. All right, 1.26. So you're going for the row that's 1.2, and you're going for the column that's 0.06. And so you want to see where those match. So 1.2, and then right here, I'm in the column of 0.06. So it looks like I'm going to get 0.8962. Are you guys looking at the same number? 0.8962? Okay. So that's the row for 1.2 and the column for 0.06. So I'm going to take that number back to my slides. And they got this number too. All right, the next thing we do is we subtract it from 1. And we get 0.1038. And then we double it. All right, and let me see if I can explain those steps just a little bit to you. So 0.8962, that's telling me this area here, but I want the area on the right. That's why I subtract it from 1. So subtracting it from 1 will give me this area on the right. Then I'm only going to multiply it by 2 if this is called a two-sided test. If I want to know if something is neither too low nor too high, then I do a two-sided test. I do not multiply it by 2. You just use the p-value in the table if you want to do a one-sided test. We'll see an example of that one. At least we'll see one in your activity today. I'm not sure if we see one before that. Okay, so this is the number. This is the magic p-value that we are comparing to 0.05. Remember, we want it to be bigger than 0.05. Is it bigger than 0.05? I know numbers, decimals can be hard, but yeah, this is bigger than 0.05. So we're comparing it to our significance level. Since our p-value, 0.2076, is greater than 0.05, we are going to accept the null hypothesis. The statement is likely true. We didn't prove it. We just think it's likely true. And that's because 48% is really close to 50%. All right, we didn't know though, is it close enough? Is it close enough to accept it? And the significance test tells us it is close enough to accept 48% is close enough to 50% that we can accept that as our percentage. All right, this last one, it goes through some steps, but honestly, I feel like seeing the steps in the problem is a little bit easier to understand than seeing the steps written out, but feel free to read through this if it helps you. All right, and now what we're going to do is we're going to do our day 2 activity. Our day 2 activity starts with 2 problems from day 1, just like the one we did at the beginning, and then it has 2 problems from day 2. And I will be available to help you get started. When you get stuck, I'll be available. But let's work together on those.